Welcome back to Quarantine Analysis. Today we're going to be talking about continuity of functions. Before we get to the definition, I want to talk to you about some of the theorems that require continuity. Some key critical theorems in theory of calculus involve the mean value theorem, which has a continuity assumption, and the fundamental theorem of calculus, which has a continuity assumption as well. Some slightly earlier and slightly simpler theorems that we'll get to earlier than those include the intermediate value theorem and the extreme value theorem. And I want to talk to you about some simplified statements of those theorems. These statements are not complete. I mean, they're true as written, but they're not as general as the theorems should be stated. So the intermediate value theorem states that if you have an interval at AB on which a function is continuous, and the value is too low at A and too high at B, that is, there's some target value Y that we want the function to take that value. If it's also continuous on AB, then f of x will be equal to y for some x. So the basic picture that you should have in mind here for the intermediate value theorem is you have a domain A, B, on which the function is defined. And I'm not going to completely graph the function because that'll give the game away. But I just want to indicate here that the function goes from some lower value to some higher value. And somewhere in between this lower value f of A and this higher value f of B, we have some value y. The point of the intermediate value theorem is that there's no way to draw a continuous graph of a function extending from A to B without crossing that line. And when we cross that line, we have a value x for which f of x equals y. So if we draw a continuous function here, then eventually we will cross that line. And when we do, we will have a value x for which f of x is equal to y. So y is equal to f of x then. So this may seem completely obvious and common sense. This is a common sense principle, but it relies on continuity, right? It relies on the fact that we can't just skip over this value and do some other crazy thing. So this relies on continuity. We need to get a precise definition of continuity in place before we'll even know what we're really proving as we prove the intermediate value theorem. So just while we're on the topic of the intermediate value theorem, this is sometimes referred to as a Goldilocks principle. There's a value which is too low, there's a value which is too high, too cold, too hot, whatever. Then there is some value which is just right. So y is the target value, which is sort of defining for us the notion of just right. And then we guarantee with this theorem that there must be some x value, which is just right in whatever sense this function is meaning. So the intermediate value theorem may seem like a simple theorem. And in many ways, it is a very simple theorem. But it's a tremendously powerful theorem, a surprisingly powerful theorem that allows us to solve quite a number of problems that don't even seem like they're related to the intermediate value theorem. The extreme value theorem is also a very basic principle, and probably it might be something that you would assume accidentally if you'd never heard of the extreme value theorem. It simply states that if a function is continuous on an interval, a closed interval AB, then it takes a maximum value at some point x. So in other words, if we have a function defined on an interval from A to B, so this is the domain of definition, then I don't know what it's going to do here. Maybe it's going to be a function like this, and it'll take a maximum value at B. Maybe it's going to be a more complicated function. It's going to go up and down a little bit. It's going to take some maximum value here. Maybe it's going to be, very peculiar and do all kinds of crazy stuff. And somewhere it will have to take a maximum value. So the extreme value theorem simply states that a function defined on a closed interval will somewhere take a maximum value. It could be at A, it could be at B, I don't know, but it will somewhere take a maximum value. To give a complete statement of the extreme value theorem, it would be useful to state that it also will take a minimum value. Of course, minimum and maximum are basically the same principle. And that's why we call this the extreme value theorem, because it could be the extreme high or the extreme low, instead of simply calling this the maximum value theorem. All right, so these are the theorems that rely on continuity. We need a theory of continuity that we can apply consistently to functions to say, okay, these are continuous functions, these are not continuous functions. And because we're working from Ross, we will actually be using two definitions of continuity, one which we will call the epsilon-delta definition of continuity, and another which we will call sequential continuity. Let's get to the definitions of continuity. we face a basic problem here. We're working from Elementary Analysis by Ross, and which is a fantastic textbook. That's not the problem. The problem is that textbook is sequentially based, and so we need to give a definition of continuity which is based on sequences. Okay, so that's fine. On the other hand, we have a traditional epsilon-delta definition, which is kind of used everywhere else and used in metric spaces. So it's a very, very important and central notion, epsilon-delta continuity. And so the basic problem that we face is taking the approach of the textbook, which is sequential continuity, and kind of synchronizing it with the approach of everybody else, which is epsilon-delta continuity. And so instead of giving one definition of continuous function, I'm going to give two definitions of continuous function. Now, this is dangerous because if I define the same term twice, then I say, let's assume the function is continuous. We don't know what's actually being assumed. So I can't do that. Instead, what I'm going to do is I'm going to define two different terms, two sort of refinements of this term. I'm going to define sequentially continuous function, and I'm going to define epsilon-delta continuous function. And then we'll have to prove that, these are equivalent definitions. And once we know that these are equivalent definitions, we'll relax our language and we'll simply refer to that as continuous, right? And whenever you assume a function is continuous, you can pick whichever one you want. Whenever you want to prove that a function is continuous, you can pick whichever one you want. So that's kind of where we're going. But until we get that proof that these two definitions are continuous, we're going to have to distinguish them carefully. And we're going to refer to them as sequentially continuous and epsilon-delta continuous. So let's get to sequential continuity. I want to remind you, this is not going to be the definition, but just a reminder. The way we think about continuity is, the way we think about continuity in calculus, well, maybe in high school mathematics, is sometimes we think about continuity by simply saying, you can draw the thing without lifting your pen, right? I don't know how you can sketch any graph without lifting your pen, literally, but the idea is you don't lift it off the page, the whole graph becomes connected then. That's a decent sort of concept image, but that's not going to work for higher math. Another more refined definition of continuity is that if you have a sequence of x values approaching x naught, and you take the limit of f of x as x approaches x naught, then what do you get? You get f of x naught. So that's a definition of continuity that we might see in a calculus class. We might see this definition of continuity with or without a very precise definition of what that limit really means. Sometimes you'll see a university calculus class that says, that's what continuity means, but what do we mean by limit? Well, I'm not going to spell that out in detail. Sometimes you see that definition of a limit spelled out in detail. We don't have that definition of a limit yet in our course. We have limits as n goes to infinity, but we don't have limits as x goes to x naught. And so that's not going to cut it for us either. But the definition of sequential continuity is very much related to this. It's basically saying, let's consider a bunch of x values approaching x naught, and then let's consider what happens to f of those values. And then let's say, oh, well, it should converge to f of x naught. And so that's kind of the motivation behind the epsilon-delta definition of continuity. So let's get to that. So here's a definition. So let's let f be a function. Implicitly here, I would like to say it's a function from the reals to the reals, but I'm not quite saying that because I don't want to assume that it's defined everywhere, right? I want to be able to apply this definition to functions like the square root of x, which is not defined for negatives, or 1 over x, which is not defined at 0, or arcsine x or something. So I want to be able to apply this definition even if the function is not defined at all real numbers, and so I'm not going to assume that the domain is the real numbers. So let's let f be a function, and let's let x naught be in, we'll just write the domain of f. Okay, so basically I'm saying, let's just assume that f is defined at the point x naught, right? Here I'm writing DOM for domain. The domain of f, whatever it is, x naught is going to be a point in the domain. So we say f is sequentially continuous at x naught. So there are a lot of words here. We're defining sequentially continuous at x naught. We say f is sequentially continuous at x naught if for any sequence an in, well, let me say in the domain of f converging to x naught, the sequence f of an then had better converge to f of x naught. So the idea here is this is how you identify continuity. What you do is you identify a point at which you want the function to be continuous. Then on the basis of that point, you say, okay, let's think about a sequence of values, any sequence of values converging to that point. And then having that sequence of values, we get f of each of them, which gives us another sequence in the range, right? And that might converge like this, right? Now we have a value f of x naught here. So this would be f of x naught. We take this red sequence, which is the an sequence. I should probably have braces there. So we take this red sequence, which is an. We evaluate the function at all of its terms, and we get this blue sequence, f of an. And then if the function is indeed continuous, what do we expect of the blue sequence? As the an's get closer and closer to x naught, these x values are getting closer and closer to that key x value here. So the y values, well, they're supposed to get closer and closer to the key y value, which is f of x naught. Now, if the function is not continuous, of course, then, you know, all bets are off, right? If the function has this weird jump discontinuity here, so that f of x naught is not going to be there at all, but it's going to be somewhere else entirely, then the blue sequence f of an will converge, but not to f of x naught, right? Or it might not converge at all in this case. So, so if the function is not continuous, then this blue sequence will detect that. It will sort of say, oh, well, the red sequence is converging. These x values are converging to x naught, but the corresponding y values are not converging to f of x naught, and that's suspicious, and that's a failure of sequential continuity. But if the function, let's repair my function here. If the function is indeed continuous, then we certainly expect that wherever f of x naught is, as these red values get closer and closer to x naught, the y values, the blue values will get closer and closer to f of x naught, and so that's what we expect. So that's basically, we're using sequences to detect continuity. Why? Because the whole structure of the way that we've reasoned about numbers is based on sequences, right? So much of our work is based on sequences, and so we're using sequences to detect continuity. This is not the only way this is not the only game in town, but it's a good way to detect continuity. And we're going to call this sequentially continuous at x naught. Notice we're assuming the sequence converges to x naught. It might be sequentially continuous at x naught for this x naught, but then if the graph has some other crazy behavior going on here, then we might have a different point at which we don't have sequential continuity. So sequential continuity at x naught specifically refers to this point. We have continuity at this point. At a different point, we might have discontinuity. So we could imagine a graph that has lots of peculiar behaviors here, and it might be discontinuous at some points, and it might be continuous at other points. Like, for example, these might be continuous here, but discontinuous at this value, and discontinuous at this value. So, so this is kind of like at x naught. Now, we want a definition of just simply continuous, right? Continuous without qualification. So we're going to give a definition of sequentially continuous without qualification about where. So, so we say f is sequentially continuous just period unqualified if it is sequentially continuous at every point in its domain. So basically, you just say for all x naught, right? If it's sequentially continuous at all at x naught for every x naught in the domain. Well, then it's sequentially continuous everywhere, or sequentially continuous on its domain. So we simply say it's sequentially continuous without qualification about where. So that's our definition of sequentially continuous. Now I want to give a competing definition for continuity, a different notion which also wants to call itself continuity, which later we will prove is equivalent. So what's this competing notion? The competing notion is epsilon-delta continuity, which is a very standard notion. And so let's get to that. So I want to put it here because I want to compare it to sequential continuity. But then I'm going to erase that definition so that we can represent it in pictures. So let's give a competing definition. So again, let f be a function. And again, its domain might not be all of the real line. Again, we're going to let x naught be in the domain, and we're going to try to define continuity at x naught, but we're going to give a different definition of continuity. So we say f is epsilon delta continuous. Now, honestly, like I have to warn you here, if you go look up the definition of, if you go look up, you know, how do mathematicians talk about continuity? They don't talk about this function is epsilon delta continuous. You'll never hear anybody say that. We're just introducing this language as a preliminary language before we prove that that definition is equivalent to that definition, right? So in the you know hour or so that it takes for us to get all these definitions put together and prove that they're equivalent, we will use these specific terms to distinguish between sequentially continuous and epsilon delta continuous. But you don't hear this language, you won't see this language of epsilon delta continuous. You won't see that in the literature, or if you go look up other sources, you'll see this simply called continuity. But until we prove those equivalences, we need to distinguish carefully. So we say f is epsilon delta continuous if, okay, so what's the definition? Well, we simply say for all positive epsilon, there exists a positive delta, such that for all x in the domain of f, if x minus x naught absolute is less than delta, then f of x minus f of x naught absolute is less than epsilon. So this definition should look very unfamiliar and very familiar at the same time. So this is a completely new situation, but this definition has an awful lot in common with our usual definitions of limits as n goes to infinity. So it starts with for every epsilon, and then it, I should say, I have said then here, but I want to say implies. So if this, then that, in other words. So it has the same basic overall structure of the epsilon n definition of the limit of a sequence. We have for any epsilon, there exists something. Now in that definition, there exists a cap n, and so here there is a delta. So what exists is different. And then for every, right, for every little n in the naturals, for every x in the domain of f, so we have that same definition, and then a constraint about what it is that's quantified here. And then if that is true, then we get some proximity less than epsilon. So this thing has a lot in common with epsilon n continuity of sequences. And that's actually really good news. It is fundamentally different. It's not the same thing, but that's good news because that means that all of your training proving epsilon n limits for sequences, a lot of that is relevant to, okay, how are we going to prove this, right? We're going to prove this by letting epsilon be greater than 0, and then we're going to continue by trying to choose a delta and probably leaving that portion of the proof blank for a little bit because we don't know how to choose the delta, and we'll get to that later, and then, you know, letting x be in the domain and assuming this, and then trying to do some algebra with inequalities to establish this. So that's kind of how to straightforwardly prove this definition, and it has a lot in common with that epsilon n definition. I forgot here that I was doing this at x naught, so I need to add that. So that's at x naught. So we're defining epsilon delta continuity at the particular point x naught, and I left that out. Sorry about that. So that's epsilon delta continuity at a given point, and then we have to do the same thing here to define epsilon delta continuity just sort of at large. So we say f is epsilon delta continuous without qualification about where, if it is epsilon delta continuous at x naught for all x naught in its domain. So this is the usual thing. We drop the at x naught if it is so for all possible x naught, if it's continuous on everything in its domain. And so, so this is our epsilon delta continuity. Now, I want to try to convince you that this does somehow represent continuity. When you look at these epsilons and deltas, you know, if this is your first time seeing this, then maybe you're like me. It just looks like a complicated logical mess, and it doesn't seem to say anything about I can draw the function without lifting my pen. So basically, I want to draw a couple of pictures, and I want to gesture at the pictures to convince you that this thing at least has something to do with the values of the function are continuing, right? This is our official definition, and we have to just there's no proof of this definition. It doesn't make sense to prove a definition. But I want to kind of justify that this really is somehow detecting something about the graph is continuing, right? The graph is not jumping. So let's look at a graph of a function which is continuous, but then, oops, it has a break. And then it's continuous. So let's examine this important point. I'm going to call that x1. And then I'm going to identify another point over here, x0. And then we're going to examine this function's behavior near x0. And we're also going to examine this behavior near x1. So here, let's actually, let me move x0 slightly because I've caused a coincidence that f of x0 is almost exactly equal to f of x1. So let's adjust the graph a little bit. And then we'll put x0 here so that we can easily distinguish between f of x0 and f of x1. So here's f of x0. And then if, that's, I was wrong. Okay, sorry for the last minute adjustments to my graph. Let's move that up because this is the close point here. So f of x1 is actually way up here. So there's f of x1. Okay, so we have a value f of x0 and a value f of x1. Now, to understand this logical form, it's actually quite helpful to read it backwards here. So what I want to do is I want to focus on this, right? If you think about the sequential convergence definition, the most important thing is a sub n minus L absolute less than epsilon, which is telling you, like, if you're having a sequence that converges to a given point L, and you want to understand what that means, that's the most important part of the definition because that's the part that tells you that the terms are close to L, right? Epsilon is a measurement of how close you need to get, and this is basically saying that the terms of the sequence have gotten close to L, right? So this is the most important thing to understand, and there's a lot of logic to understand besides that, but that's really the crux of a sequence converging to L. So the crux of this is right there. The most significant part of this definition is this statement. And so let's try to figure out what that means. So epsilon, well, you've been doing this for a while, so you know that epsilon is going to represent some small number, right? So how do we draw epsilon if it's supposed to describe the possible distance between f of x and f of x naught? Well, f of x is a y value, and f of x naught is a y value. F of x naught is this y value here, and f of x is some other y value. And epsilon is how close they're supposed to be. So when we read this, we need to interpret this as having some, I mean, this is a vertical, like this is a height on the graph. This is a height on the graph. And this is the proximity between two heights on the graph. So epsilon should be plotted vertically here. Basically, epsilon is telling you there is some vertical leeway here. Now, to think about epsilon really ideally in your head, you should probably think of epsilon as an extremely small number. And I would draw it extremely small here, except that if I draw it extremely small, you won't be able to see it. Okay, so imagine that my epsilon is especially tiny. Okay, now in any event, the epsilon will give us some sort of window of opportunity here. The epsilon will define a range of y values. And it is within that range of y values. Let me actually, it's a little hard to see. Let me shade it in red. That range of y values basically represents the constraint that f of x, that's right behind me there, that f of x minus f of x naught is less than epsilon. So that constraint is represented by that red bar in that picture, in that that's the set of all x values. Well, that's basically representing the possible y values that are within a distance of epsilon from the target y value f of x naught. And so that's kind of representing that. Now, how do we represent this? This is basically telling us that we have a delta here, but notice that delta is the difference between x and x naught. So delta is basically a horizontal distance between this thing going either side of that. So the delta window is kind of telling us, okay, there's a horizontal distance here, that if you are within this distance of x, and notice there's a horizontal window and a vertical window, and they kind of relate to each other. And that's basically what the epsilon delta definition is all about. It's about the relationship between this constraint on x, saying that x is close to x naught, and this constraint on f of x, asserting that f of x is close to f of x naught. And now it's time to read the rest of this. Basically, let's focus our attention on this. For any epsilon you pick, there is a delta. This existence of delta as depending on epsilon is the key here. It basically is telling us if epsilon is given, so let's not draw these at the same time. Let's think about them as coming one at a time. If epsilon is given, no matter what the value of epsilon is, if epsilon is given first, then what we have to deal with is, here's our function, and here's our vertical window. And this is the given information. If epsilon is already given, then there must be some delta, then there exists a delta. So in other words, on the basis of the value of x naught and f of x naught and epsilon, once all of that is given, then it is possible to draw a delta window here. So this is a horizontal window, which creates this vertical bar here. And then what is special about that delta, as long as x is within this window, that is here, as long as x is somewhere within here, then y will be within its required window. So focus your attention on this whole portion of the graph here as delineated by these blue lines. In this portion of the graph that's cut off by the blue lines, that portion of the graph is within the red lines. And why is it? Why is it entirely within the red lines? Because the function is continuous and didn't vary very much along this blue window. So we were able to choose this blue window, which is the delta window, so that that portion of the graph got entirely within the requirements of that red window. And that's what we really needed to do here. And so this is basically the red window represents the epsilon and this condition. The blue window represents the delta and this condition. And if the epsilon is specified ahead of time, it is possible to draw that blue window so that everything matches up. Now let's contrast this with the other case. So what I'm going to do is I'm going to erase this entire portion of the graph, and we're going to focus on x1 instead of x naught. Okay? And we're going to ask ourselves, so this portion of the graph no longer matters. We're going to ask ourselves, is this function continuous at x1? Well, I mean, if you look at the graph, obviously not. But the real question is, how does the definition of continuity capture the failure of continuity here? So how does this not work when we use the point x1? So, well, if you believe this business about the windows, then this is f of x1, and we can choose some epsilon window above and below that, which will produce a region of interest. And this is basically, this region here basically represents the requirement f of x minus f of x1 less than epsilon. That's basically this region is sort of a picture of that condition. So I've picked an epsilon, and there's that window. Now, if this is going to work, then I'm supposed to choose a delta, some very small delta. So let's actually choose a really big delta first. There's supposed to be some delta. And then on that delta, if I use that delta to determine a small portion of the graph, then the portion of the graph that I can identify using that delta will lie entirely within the red window. And you can see here, well, it doesn't. But maybe it doesn't because I chose delta to be a really big number. And maybe if I choose delta more judiciously, then I can do a better job getting the requirement that I need. So instead of choosing delta to be this huge number, what happens if I choose delta to be a fairly small number? So this will be sort of more relevant. The question is not, does every delta work? The question is, does there exist a delta that works in this context? So let me repair my graph here, and then we'll examine this question. Does there exist a delta that works? Well, no matter what delta I choose, I'm going to get a window that includes some portion of the graph here on the left. This portion of the graph up here is fine. That's good news. That thing lies within that window. But if I'm going even a very tiny amount of distance to the left of here, then I'll pick up a portion of the graph which is over here. And that portion is bad news for the epsilon delta definition of continuity. Why is it bad news? Because it's a portion of the graph that satisfies this, but doesn't satisfy this and makes the implication false. Yes, x minus x naught is less than delta, but f of x minus f of x naught is not less than epsilon. It's entirely outside of this less than epsilon window. And so this is actually what we want to happen. This function is discontinuous here, and we want to see the discontinuity as a failure of this thing. So these two pictures, this one and the previous, are an attempt to convince you that this thing really does represent this feature of a graph that it continues and doesn't jump. Of course, continues and doesn't jump is not our official definition. This is our official definition, and this is just all motivation to help you understand what it means. So let's sketch the roadmap of where we're going next. Now that we have two different definitions of continuous at x naught, then, well, the natural question is, how are they related? And the answer, not to leave you with any cliffhangers, the answer is they are logically equivalent. And so the next thing that we need to do is we'll prove that they're logically equivalent. And then knowing that, we will drop the complicated language of epsilon delta continuous, sequentially continuous, and we will relax, and we can just call both of those conditions continuity.